So this is about prospecting for oil and gas. Fundamentally, as I said, historically, it's not been easy to find. There's kind of a sense that we've certainly found as much oil and gas and coal as we need, is the sentiment. There's more technology being applied to get better recovery factors out of what we've already found. But 40 years ago, when I was in this class, it was hard to find oil and gas. And it was viewed, as I mentioned before, as very scarce. So our tools have gotten better and better, and we're really in a place of optimizing recovery of these resources from the subsurface. And there's still some big exploratory drilling going on, but it's much, much less than it was 40 years ago. So, and we live in a world today where California has banned new drilling for oil and gas, okay? And there are much more restrictions on new development. I mean, there is an offshore lease sale that Biden's catching a lot of flack for right now. And so there's this gray area that he's trying to navigate around allowing, when I took this class 40 years ago, the United States was importing over 60% of its oil. Today, we're a net exporter. And so there's an argument that whatever money you're not spending to develop your own domestic resource, you're spending on military to defend access to the resource in other countries. So that's a point I have not made that's really important about fossil fuels. They do not occur as equitably in the world as the wind and the sun does. So that geologic history, those moving tectonic plates, mean that a handful of countries have a disproportionate amount of a resource that for coal and electricity, for oil and transport, that's created a lot of geopolitical tensions that the history of oil and gas lecture that you watched before class goes into in more detail. But I think that limited distribution has caused a lot of conflict and has caused a lot of countries to say, we're going to invest deeply domestically and create these subsidies rather than be subsidizing military resources to maintain access to it from other countries who then hold power over us which is what was going on when I took this class in 1980. There were big political crises around access to oil. And we're going to talk about geologic processes, which is how do we find this stuff, the Sherlock Holmes of where does this occur. We're going to talk about conventional versus unconventional. I will look you in the eye and say, even though I might look very conventional, I prefer to be unconventional. And I would urge all of you to explore as far outside the box as possible. But here we have key meanings. Fundamentally, conventional resources of oil and gas have porosity and permeability. Unconventional resources lack permeability. You have to do something that you induce to create permeability to get the oil and gas to flow. So that's the fundamental, but we'll get into that in a bit more detail. We're going to talk about the tools, much the kind of radiology, if you will, of oil and gas. How do we see the subsurface? And then we're going to talk about some of the rules. So this lecture is going to cover this area of exploration, permitting, leasing, and land. On Wednesday, we're going to get into drilling and completion, and Diana is going to talk about the last two chunks of this process. So prospecting, we're going to talk about oil and gas rocks. So one of the big ideas when you think about oil and gas that still is hard for people to understand, it does not occur in underground swimming pools or caves. The rock that holds oil and gas is like a brick. And in the pore space occurs oil and gas, and you look at it and you say, how could we get anything out of this? But that's what a typical reservoir looks like. So the picture you see here is a conventional reservoir. When I went to Stanford Business School long ago and far away, there was a decision science class, and the most classic question in decision science was dome, no dome. Is there a dome or not? So what you see there is a dome in geology called an anticline, because one of the most common ways we found early oil was to find situations where flat rocks were folded due to compression, and oil migrated to the highest point due to the density of the oil and the water pushing, the ancient water pushing underneath it. And we're going to learn in the next couple lectures about produced water. And so there's an oil field down in Southern California we sometimes take students to, but most people don't realize that most oil fields, the majority of what gets produced out of the wellbore is ancient water. And the water is pushing up underneath the oil. And we'll talk more about that. But that's a conventional diagram. These are pictures of sedimentary rocks Shale, sandstone, limestone, dolostone it's called. 95% plus of all oil and gas occurs in sedimentary rocks. Same with coal. Coal essentially is a sedimentary rock. So, and you've got my note there, it does not occur in underground swimming pools. Very few oil and gas accumulations are in limestones, in carbonates we call them, but some are. But most are in shales and sandstones. So the other kinds of rocks you all learned early in your lives are igneous and metamorphic rocks, and it's very, very rare to find oil and gas in those rocks. If they did, they migrated in there under kind of unusual circumstances. So there's a lot of words on this slide, but when you think of an oil and gas resource, the two most important words are porosity and permeability. In that rock, how much pore space is there and as a volume of the rock, and permeability is the ability of the pores to be connected and for a fluid or a gas to move in those pores. So those are the two, and there's a great, Mike Ming is a guy who was a teaching assistant with me 42 years ago. We are still really good friends, and he's a petroleum engineer, and there's a really good 2-minute video there explaining permeability and Darcy's Law. So if that's a new concept to some of you, or many of you probably, it's an entertaining way to be exposed to it. So conventional reservoirs have permeability, unconventional reservoirs do not. So we're going to talk a bit about anatomy of an oil field. Again, this is a dome kind of story. This is a conventional reservoir. It's showing oil migrating from where it was buried and subjected to time, temperature, and pressure, and migrating over time. One of the breakthroughs we had, if you remember I talked about dinosaurs to dead algae, is we figured out we could actually date and match fingerprint rocks from western Wyoming, where there's thrust faults and faulting and lots of burial, and we could fingerprint the source rocks there to oil fields that were in eastern Wyoming. And we could see the rock that the oil had migrated through. So geologists do that kind of sleuthing to put that all together. So we talk about traditional or conventional oil and gas fields in terms of having a seal or a cap rock on top of a reservoir rock. And then for those of you that have made salad dressing, you know that oil floats on water. And so and gas is lighter than oil. So if you have oil and gas and water in a rock, you tend to have the gas on top, you tend to have the oil, and then you have the ancient water from that woody, peaty, planty swamp that got buried with time, temperature, and pressure. And that water is often a brine. It often is not pure drinkable water. It's water that's been around for millions of years. And so disposing of that water properly when we drill is a really important part of the story. So this, if we were looking under a microscope at a reservoir rock, this is giving you a sense of what a conventional reservoir would look like, which would have a lot of porosity, a lot of permeability, an unconventional reservoir in the middle, and something completely unattractive for extracting oil and gas from on the left. So it says here, one of the ways to think of a good reservoir rock, it's like a rigid sponge. So it has pore spaces in it and things can flow through it, but you're not going to squeeze it the way you would a sponge. But visually, that's a way to think about it. So this is a picture showing unconventional reservoirs, shows a directionally drilled well or a lateral well bore, which is different than a horizontal one here. We'll get to horizontal in a little bit. But unconventional reservoirs include coal bed methane, which is coal beds too deep to mine from, but we can actually extract gas out of. What we call tight sand reservoirs. And this is just giving a sense of the different geometry of unconventional compared to conventional on the upper left. So I'm saying the same thing many times. It's really about permeability. And all industries get bogged down in a lot of nomenclature, and this is just highlighting when we talk about oil, we also mean petroleum, and we have conventional and unconventional, and then we have lots of subnames here, and we're not going to try and trip you up on these subnames. It's more to help you decode when people say oil shale or shale oil or heavy oil or tight oil, what are they talking about? Because it's super confusing, even for me who's been exposed to the industry for a long time. And with natural gas, we have our conventional sources, which we'll talk more about on Wednesday. We have unconventional, which has really been a game changer in the United States. Most of our wells are horizontally drilled now. It's true for oil as well. Then we have this very large resource of natural gas, which is a little frightening, is it's largely trapped in ice. And as ice is melting, we are exposing lots of methane. We don't know how to harvest it commercially. Japan has done more research than anybody else, and there's a slide at the back of our natural gas deck that talks about this. But it's more when you hear people mention methane hydrates are part of the story of natural gas. So we have all these labels. So this is not put here to scare you, it's put here to orient you. Going back to conventional, there are many kinds of traps. And until we figured out how to drill horizontally, people who are trained like I was trained were trained to look for these kinds of traps because that's where oil and gas would most likely occur. Turns out thinking about these traps is useful for looking for lithium reservoirs. It's used in brine. It's useful for looking for other things too. But this kind of understanding of geology was largely applied for oil and gas exploration. So structural traps, it can be folds, it can be faults, it can be a salt dome piercing sedimentary rock, and that creates a trap. Or there can be what we call stratigraphic traps, where you have sediment deposited like this, and then it gets tilted, and then it gets eroded off, and that creates a seal. But there's no faulting associated with a stratigraphic trap in general. So my kids would say, Mom, this is way TMI. These people don't need to know all this, but it's just orienting you to the way people thought about conventional reservoirs. So I have a note about this picture. This is what in geology land we call a road cut. In civil engineering, it is that. It's a road cut. You cut through a hillside to put a road through, right? For a geologist, a road cut is a little bit like what a cadaver is to a med student. A road cut is an opportunity to see what's going on, to open things up. It's one thing if you're a doctor or a med student, you look at a body, but that you have to cut in to see what's inside. And as a geologist, part of what's really challenging about anything that we're mining out of the earth is we have so few data points. And so this is just to highlight the fact that one of our tools for identifying oil, gas, geothermal, anything in the subsurface is trying to understand what's going on in the subsurface, and road cuts are one of the ways where we can get some clues. A key thing when you think of people who are explorationists for anything in the subsurface, oil, gas, geothermal, anything, is there's a bunch of parts of our country and other countries where you just can't do anything anyhow. So if you're thinking about, I want to go look for oil and gas, first of all, you have to say, well, where could I look for oil and gas? Because a bunch of areas, for very good reasons, have said no, not here, including the state of New York has said no oil and gas. It has a history in oil and gas, but they are not allowing any drilling at all. And they got to that way ahead of California. So first you look at where are things, you're not going to go drill in Yosemite, right? Things like that. So the key tools is we look for, so surface mapping would include road cuts and being able to see things and just being out in the field. I used to get dropped in the field in a helicopter to go make maps out in the Rockies when I was 22 or something like that. It was very exciting, but you're literally looking for puzzle pieces to put together to try and understand the subsurface. So this is a list of the things we use, and that is a thumper truck used to collect geophysical data. We basically are sending sound waves down into the earth to get the equivalent of an MRI, and that is part of the data collection. So as I say, geology and geophysics are a little like internal medicine and radiology for the earth, and so those sets of disciplines are really important for understanding what's going on below. So these are examples of, so we use big regional maps. This just happens to be an image of a regional map of California to help you understand where you are in the context of plate tectonics and what's basins, what's range, what's mountain, what's going on. And then a really powerful tool is a discipline of paleontology, where it turns out, for people who know a lot about biodiversity and the history over time, is there's steady evolution going on. And so there are people who've done fantastic work in their databases where microfossils help us understand. As we're drilling down to a rock or we see it in a road cut and we get a sample, we can put a tag on that, either a carbon date or a fossil date, to know what that is. Because when you're in the subsurface or looking at the subsurface, you're trying to tie everything together and you can't see very much. So this is very important. So the geophysical profile you see on the upper right is what I used when I worked for ARCO, which was like a very primitive X-ray. It was 2D. Computing power was really slow then compared to what it is now. And now this is a 3D visualization you see on the lower right that's more like a CAT scan. And they now actually have simulations where you can walk into a room and you can pretend you're an oil molecule, and they can blow it up so you're like, you as a person can pretend you're migrating through a pore space. It's amazing what they've been able to do with VR and things like that. But the fundamental idea is we're sending sound waves down to the Earth, and different rocks have different densities, and that difference in density gets reflected back in terms of the images that we're able to produce to map and understand what's going on. Another tool we have is we've literally drilled, hundreds of thousands of wells, and even if you don't find what you're looking for, a definite practice is to use wireline tools and drop tools down the wellbore and collect a lot of data about what we've drilled through and what's down there. So companies like Schlumberger, Baker Hughes, hopefully that you've heard of, those companies are specialists in that arena of subsurface logging. And Schlumberger, Halliburton, Baker Hughes, Weatherford, Pioneer Wireline, those are all companies that specialize. And we collect these, and these fall in the public domain too. So they're literally, each state has log libraries, and you can access these logs and use it to do exploration and try and triangulate in the subsurface and figure out what the heck's going on. The other really interesting thing is this is a very US biased conversation, so I apologize, but we are the largest producer of oil in the world. And states get a severance tax off the top of oil production from any well. So they collect that tax, and they sometimes collect an ad valorem tax that's like a property tax for the value of something in the subsurface. They use those revenues largely to fund the regulation of the industry, but other things as well. Sometimes the severance taxes help fund school programs in the state and things like that. But as part of the regulatory process in these states and this tax that's being paid, in order to ensure that the operators are paying the tax properly, a lot of production data gets created. That production data is collected by multiple companies, including a company called IHS Energy. There are several other companies who do that, and they scrape the data that's in the public domain, and they make it available on subscription platforms so that as an exploration geologist or a production geologist or a geophysicist, you can pull together production data, see it on a map, and it helps give you ideas about where to go and drill or not drill or what's going on. So all that data that you see there, I operated in a world where literally every month we used to get bankers' boxes full of phone books like data that we had to go through manually to try and understand what's going on. So our ability to manage high volumes of information and get insights from it has gone through a real revolution in my 39 years, she said sweetly. Land rights and regulation, this is really important, and it applies not just to oil and gas. If you want to build a solar project or a geothermal project, you need to have access and control to the land that you want to do something either subsurface or on the surface. So this is a career path that many people don't know about. There's something called a title attorney whose job it is to help render opinions about what do people really own in the subsurface or on the surface. There's a profession to be, so in order to have any oil and gas or geothermal or wind project take place, you need to engage a landman. That could be a woman or a man, but it's the profession just like fireman, it's called a landman. And their job is to understand and get control of subsurface or surface land to be able to develop projects. So we're going to dig in. So this is kind of a highlight picture that shows, so I've already identified professions associated with this activity are title attorneys and landmen. We need it, so even for carbon capture, utilization, and storage, you need to get access to the right to the pore space to inject CO2. So here you need understanding of all that. So land rights are essential really to any form of development. And an important part in the United States is you end up in interesting situations where the surface owner, who's a rancher, can own the surface, but someone else can own the minerals, and someone else can own the water rights. They can be severed. So it turns out that that's a very interesting thing to try and keep track of for everybody, and that's where the title attorney and the landman come into play. And in some cases, people will say you can have a coal lease, and so you're just leasing the right to the coal, and someone else could be leasing the right to oil and gas. It's unusual for them to occur in the same stack of rocks, but I'm just saying they're separate rights that end up being sliced off for people to do development. So The rest of the world, it says outside the US, there's one type of mineral right ownership, the government owns it. That hasn't been the best thing for commercialization of subsurface resources in those countries. They usually have a license, is the term used. Occidental Petroleum, Armand Hammer pioneered, he came into certain countries in Africa and offered to drill water wells in exchange for a concession, it was called, to the right to drill for oil and gas in those countries. So again, you're negotiating with the government. In the United States, we have 4 types of land you see here. The most common place for resource development to take place is on private land. The second would be federal land. And the Department of the Interior and the Bureau of Land Management largely manage that. So you see the potential severing of surface rights and mineral rights. And so if I own mineral rights and Chevron wants to drill on my property, they have to persuade me to sign an oil and gas lease where I would get money up front, and I would negotiate today in the active basins like the Permian, I would probably get a quarter royalty. That's how active that play is. So in areas that are less active, the minimum you would get royalty you would get as a mineral owner is 1/8 royalty, and you bear no costs. You have no environmental risk. You just get an 1/8 minimum and as much as a quarter off the top for anything that's happening on your property. That lease you sign has a term to it of like 5 years, and if they don't do anything, the full rights revert back to you. We could do a whole sidebar on the nature of land rights. So there's 2 main things that are really important is you have to have clear ownership or title, or someone can challenge you and say, whoa, 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 you thought you owned that. You bought that or you leased it, but you didn't. You got to prove it. So there's a very strong proof test around ownership and getting control of an area you want to develop for wind, solar, whatever on the surface or in the subsurface. But a huge thing, I'm going to kind of go to the bottom, is you can't do anything if you don't have a social license to operate in a community. Down at the bottom it says here. And so everybody in this class needs to know 2 acronyms. NIMBY, not in my backyard, but the more important one is BANANA, build absolutely nothing anywhere near anything. So the default, whether it's a data center or a Walmart or whatever it might be, or a geothermal project or an oil and gas project, the default of humanity is banana, don't do it, right? So if you want to get something developed, a carbon capture project, whatever it might be, you've got to learn how to engage the community and create a win-win situation. And landmen, not title attorneys, but landmen, and whether they're men or women, end up doing the things you see over on the right-hand side. Very important part of it. So regulation is abundant in the United States. It wasn't always that way. There are federal laws, there are state laws, there are municipal laws, and there are, when I say municipal, I mean county and city laws. So you see the range there, and we have tribal laws too, because all our Native American tribes are sovereign nations. There is oil and gas development on tribal land, but only on their terms and with their agreement. So this is a list of all the kinds of things that are regulated. The process is extraordinary, honestly, and you have to staff deeply to manage the regulatory process. Is the regulatory process perfect? Absolutely not. But it's so much better than it was 30, 50 years ago. And so it goes back to the poop issue, is a lot of the fossil issues we have from legacy are the fact that we didn't have the regulation we have today. We have the Clean Air Act, we have the Clean Water Act. We have a lot of those really good things. They actually do regulate this, but it doesn't really show up on the list. Some of the videos that you're going to watch between now and Friday, there's a Shell video if I remember properly. Ultimately, there's an obligation to reclaim the site. So when you're done, ultimately, this oil and gas production needs to be, the wells need to be properly abandoned, and it needs to get turned back into something that could be a soccer field, something that looks attractive, right? So there's a lot of regulation. Historically, it wasn't as good as it is now, but it's pretty darn good now. And a tricky thing, anywhere you are in the world, you can have good regulation, but if you don't have the staff, and we have a national, if not global problem of training and staffing and retention, if you don't have the organization to enforce the regulation, then you don't end up where you want to be. And you have to keep the regulatory bodies from not being corrupt either, no matter what it is you're regulating, whether it's banks or medicine or oil and gas extraction. So these are examples of the regulating organizations. Some of these are federal. I think we've got the Railroad Commission in Texas. We've got the Colorado Oil and Gas Conservation Commission. So state by state, the state organizations have very different names. The idea that the Railroad Commission manages oil and gas in Texas is not intuitive to people. But a lot of railroad land in Texas got developed for oil and gas, and that's part of the root of that story. And obviously, the Bureau of Ocean Energy Management, which manages offshore oil and gas development, they also are managing offshore wind. BOEM is also managing EV metals extraction off the ocean floor. So that's an agency that's going through a lot of change now because its history was largely oil and gas. So this is showing you where the federal land is in the United States. And we're in an interesting position right now where we have Secretary Deb Haaland, who's a Native American, a native of New Mexico. New Mexico is a prominent oil and gas state. You can see New Mexico has a lot of federal land, so she's a great Secretary of Interior to be navigating and managing some of the issues we have around federal lands. The role of federal lands in oil and gas production is declining, just due to the natural evolution of the biggest action with horizontal drilling is in places like Pennsylvania, North Dakota, and Texas, which are places that are not dominated by federal lands. So it's more of a legacy story there. And so this is something that's been around for a long time. 1960, Eisenhower created the Arctic National Wildlife Refuge. Jimmy Carter enlarged it. And depending on whether there's been a Democrat or a Republican in the White House, it's been, let's reopen it. No, let's close it. Let's reopen it. No, let's close it. But as the notes for this slide talk about basically all the major sources of financing for anything near the Arctic in terms of new drilling, they've all said we're not going to do it. We don't need, in this world of peak oil is going to be determined more by demand than supply. We have a lot of oil in the lower 48. So for right now, the Arctic National Wildlife Refuge is a quiet spot, but it's a place that has had a disproportionate amount of news. It's very, very, as you can see, it's almost adjacent to Prudhoe Bay, which you see up in the upper left. So, but that's an example of, we said we were going to protect, oh, maybe we're not, so it's political. So this is meant to summarize to my friend here, I've highlighted in yellow, the biggest subsidy we have to oil and gas is there's no price on carbon. That's the implicit subsidy. The explicit subsidies are listed up here and shown in the graph on the right-hand side. So there are explicit subsidies, and there the trade-off is a bit of, if we don't subsidize it, we will go to war, which is another form of subsidy to protect our access to it until we come up with a better technology like electric vehicles and the supply chain we need to support electric vehicles that diminishes our dependency on oil. So we're in the midst of that transition, obviously, but until we make our way through that transition, part of the challenge of how subsidized both implicitly and explicitly oil and gas have been is it makes it that big a hurdle for renewables to compete with relative to the legacy. And the subsidies for oil and gas are relatively permanent, and the subsidies we've had for renewables which we'll talk about more, have tended to be intermittent. So the perception of the public is renewables are wildly subsidized and fossil fuels are not, and that's actually not the case. So this is just meant to wrap up what we've discussed, which is to highlight, we have these geologic processes, time, temperature, pressure, an organic material, that biological, biomass origin, this is chemical energy, and there's a lot of medical-like metaphors for the sleuthing process. The human body stays pretty static, though, so we don't have the same issues we have with geology and looking at the Earth, that we have to imagine where were things tens and hundreds of millions of years ago and where are they now. It's an interesting part of it. Everybody here knows that unconventional means there's low permeability. We reviewed the tools largely that are used, and just to highlight there, we're going to talk more about offshore and oil and gas, and the tools we use offshore. We do seismic in the offshore. It's just instead of a thumper truck, we drag tools that have sound waves behind a boat to collect geophysical information that way. So it's just a little more complicated offshore than it is onshore, both to explore and to drill. But some of the resources offshore, we tend to have some very large fields offshore that are just part of that geologic history and how the plates and the accumulations, where they were in the past and where they are now. The land and regulation part, I'm hoping I've given you a sense, at least in the United States, about how that's organized at a high level. And like we always try and do, there's a lot of information here to let you dive into, including more information to highlight distinctions between upstream, midstream, downstream, and other good stuff. I think with that, I'm going to give it a wrap.